Hello, my name is Mr. Asprey, the only maths YouTuber to have a elite ranking in Foot Champs, and today I'm bringing you October 2020 mechanics paper. So let's get into it. Question number 1. We have a rough horizontal plane, which means there will be friction. It's inclined at an angle, and you're given the angle. A brick P of mass m is placed on the plane. The coefficient is mu of friction. P is in equilibrium on the point of sliding down the plane, which means friction will be at its maximum. Models of the particle, yada yada yada. In terms of m and g, the magnitude of the normal reaction to the plane. So the first thing we're going to need to do is draw a force diagram. So I've got a angle here of alpha. I've got a object here, and that object has mass m, so therefore its weight is mg. We can straight away draw the components of this force, because we know the angle in here is always going to be the same angle as the slope, and that's mg cosine alpha because it's adjacent to the angle, and this one coming down here will be mg sine alpha because it's opposite the angle. Okay, now we are going to have some frictional force, which is going to be keeping the object from falling all the way down the slope. So that frictional force is F, and we're also going to have a normal reactional force, which is going to be perpendicular from the slope. We've also been told what the angle is, and what I like to do when I'm told it in terms of tan is, let's just remind ourselves, it was 3 over 4. So I write 3 is the opposite and 4 is the adjacent, because tan is opposite over adjacent. By Pythagoras, the hypotenuse will be 5. So that will tell us that sine alpha is the opposite, which is 3 over the hypotenuse, and cos alpha is the adjacent over the hypotenuse. Okay, great. Now, what have they been actually asked us to do? Find the magnitude of the normal reactional force. Okay, well we can resolve the forces perpendicular to the plane and use the sum of the forces equals mass times acceleration. So what forces are acting perpendicular to the plane? Well, it's just r going up and mg cosine alpha coming down. So those two must be equal, and because there's no acceleration, r must equal mg cos alpha. And what is cos alpha? We've got it over here. So that tells us that r is equal to mg multiplied by 4 over 5. So we could say that's 4mg over 5. Okay, next part is part B, and it's asking me to work out mu. It's telling me that's going to be 3/4. Okay, so let's sticking with our force diagram. And now what we need to do is resolve horizontally, or parallel to the plane, I should say. So parallel to the plane, we've got friction going that way, and we've got mg sine alpha going that way. So those two, again, because it's in equilibrium, it's on the point of slipping, it's not actually accelerating, those two must be equal. So we can say friction must equal mg sine alpha. We know that sine alpha is 3 over 5. So friction is equal to mg multiplied by 3 over 5. And what's the formula for friction? Well, friction is at least equal to, it's less than or equal to mu times r. But when friction is at its maximum, i.e. when it's in equilibrium, friction is working as hard as it possibly can, then essentially friction is equal to mu r. So here we can say that mu r is equal to mg 3 over 5. Now we know what R is, we just worked that out recently, it's 4 mg over 5. So we have that mu multiplied by 4 mg over 5 is equal to 3 mg over 5. We can divide both sides by mg and multiply both sides by 5 to get mu times by 4 is equal to 3. So therefore mu is equal to 3 over 4 as required. Okay, it now says explain briefly. Oh, hold up, no, there's more. For part C and D, you do not require any calculations, so it's just an explaining. It says that the brick has been removed and replaced with a heavier brick, and the friction coefficient is the same. Explain why the brick will remain at rest. Well, the forces are always equal to mass times acceleration. Now, will the forces still be balanced? Well, what are the forces acting in the parallel to the plane? Friction and mg sine theta, or alpha, sorry. So we'll have mg sine alpha going one way, and that will equal the frictional force, because the frictional force is mu multiplied by r, and remember r was mg cos alpha. So essentially the m's will cancel, therefore the heavier mass will not upset the equilibrium. Okay, next question. It says the brick is now projected with a speed down the line of the slope, and the brick is modelled as a particle. Describe the motion of the brick, giving reasons for your answer. Well, it's now got initial velocity, but again, we've already shown that the acceleration will equal 0, because these two things are going to be balanced still. So because it's still in equilibrium, the brick is still in equilibrium, therefore will continue at constant speed. Okay, question number 2. A particle moves with acceleration. Note that this is not with respect to time, so this is actually constant acceleration, which is going to be helpful. It means we can use SUVATs and we don't need to integrate or differentiate. At time t equals 0, the particle is moving with that. Okay, so straight off I can start by writing SUVAT. And I have that the initial velocity is minus 2I plus 2j. The acceleration is 4I minus 5j. And it says find the velocity. So I'm looking for this, and I know that time is equal to 2. So the SUVAT without an S is just V equals U plus AT. So I'm going to write them in columns, because I find it easier. VI, Vj is equal to the U, which is minus 2, 2, plus the A, which is 4 minus 5, multiplied by 2. So reading along, I'm going to get minus 2 plus 8 is 6. And then I'm going to get 2 plus minus 10, which is minus 8. So this is 6I minus 8j. At t equals 0, P passes through the origin. At t equals capital T, where t is greater than 0, the particle passes through part A. The position vector of A is lambda I minus 4.5j. find the value of t. So what we know is we know the position when in the j direction. So what we could do is we could do a suvat just for the j direction. So suvat just for j. So the position in which we hope to achieve is minus 4.5. The initial velocity in the j was 2. We don't know what the velocity is at this particular moment in time, but the acceleration stays constant, so we do know that that's minus 5. And we're looking for the time, capital T. So the suvat without v is s equals ut plus a half at squared. So we have s is minus 4.5. Minus 4.5 is equal to 2 is u, capital T, and a half of minus 5 is minus 2.5, capital T squared. So bringing it all over to one side, I'm going to get 2.5 t squared minus 2t minus 4.5 is equal to 0. And I can solve that in my quadratic equation part of my calculator. Degree 2, and we're going with 2.5 minus 2 minus 4.5, and we get 1.8. So t is equal to 1.8. Okay, hence find the value of lambda. Well, lambda is the I position. So let's figure out where it is in the I direction. So in the I direction, again, S, U, V, A, and T. We know the time what we want to inspect, which is 1.8. We're looking for this. The initial in the U, the initial velocity was minus 2 in the I direction. I don't know what the velocity is going to be at that particular point, and the acceleration was 4 in the I direction. So the one without a v is going to be s equals ut plus a half at squared, and we're going to get minus 2, 1.8, plus a half of 4 is 2, 1.8 squared. So I'll go to my calculator, and we will type minus 2 multiplied by 1.8 plus 2 multiplied by 1.8 squared, and we get 2.88, which is our lambda value. Okay, question 3. Now this one, the acceleration is respect to time, so it's not constant, so we can't use suvats, and we must therefore use integration and differentiation. So just a quick reminder, you've got position, velocity, and acceleration. You can integrate up, and you can differentiate down. So at the moment we've got acceleration, so we're going to integrate. So I'm going to integrate the I component, which is, I'm going to write it like this, 1 minus 4t, and, sorry, what am I doing? 1 minus 4t is the I, and 3 minus t squared is the j. Yes, and we're going to integrate that. So integrating the i's first, we're going to get t. So I should have put dt here, and this is going to give us the velocity. We're going to get t, and then integrating minus 4t up the power to 2, divide by the new power, so it's 2t squared. And the j's, I'm going to get 3t, and up the power, I'm going to get t cubed over 3. And we're also going to add on a constant in the I direction and a constant in the j direction. Okay, and it says that the initial velocity when t equals 0 is 36I, so we can substitute that in. So I'm going to get 36I is just 36 and 0j, and that's going to equal, well, when t is 0, we're going to get 0 minus 2 lots of 0, and we're going to get 0, or 3 zeros, minus 0 cubed over 3, and we're going to get ci cj. So therefore that tells us that ci equals 36, and there is no constant term in the j direction. And it says find the velocity when t equals 4. So let's just write down our final velocity equation in vector form. T squared plus 36, and on the bottom 3t minus t cubed over 3, and then we're going to sub in t equals 4, and we are going to get 4 minus 2 times 4 squared plus 36, so that's going to give us 8 in the I direction, and in the j direction we're going to get 3 times 4 minus 4 cubed divided by 3, which will give us minus 28 over 3. Okay, that is the velocity. Right, next it says find the value of t at the instant when p is moving in the direction perpendicular to I. It's a funny way of putting it, but if we've got j going upwards and we've got I going this way, perpendicular to I is essentially just going up into the j direction. So when is it going straight up? Well, it's going straight up when it has j velocity and no I velocity. So I want the velocity in the I direction to equal 0, and the velocity in the I direction is not that, it's this, so I want that to equal 0. So I say t minus 2t squared plus 36 equals 0. Writing that by multiplying through by a negative to get this, and okay, factorising this, we're going to get 2t and t, and we're going to get plus 4 and minus, let's give you 8 and minus 9, which is going to give you that t is equal to 9 over 2 and the negative value which we're not going to use. So t is equal to 9 over 2. Okay, it says at t seconds where t is greater than 0, a particle moves so that its position vector relative to the origin is given by this. Find the value of t at the instant when the speed of t is 5. Okay, so we need to take this and we need to find the speed. So we're going to have position and we're going to differentiate down. So that is t squared minus t and then plus 3t. So we've got t squared minus t and then plus 3t. And that is the position. So if I were to differentiate this, I would get the velocity. Differentiating the I is going to give me 2t minus 1, and differentiating the j is going to give me 3. So those are the two components of velocity, and I believe it said I wanted the speed to equal 5. And remember, the speed is the magnitude of the velocity. So to take the magnitude of the velocity, I would use Pythagoras, and I would say that the magnitude of the velocity is equal to the square root of both the components squared. So that's t minus 1 squared plus 3 squared, and we want that to equal 5. I'm going to expand these brackets to get 4t squared minus t, 2t, minus another 2t is minus 4t, plus 1, and plus 9, and then I'm going to remove the square root by squaring both sides. That equals 25. That's 10, 9 and 1, so it's 15 on this side. Oh no, sorry. Let's make it equal to 0 because it's a quadratic. So we're going to get minus 15, and we're going to get 4t squared minus 4t. And that is probably not the most efficient way of doing it, actually, come to think about it, because we could have, but anyhow, we're going to get 2t, and we're going to get minus 5 will give us minus 10, and plus 3 will give us the 6. Okay, so we're going to get t is equal to 5 over 2. The reason why I said it's not the most efficient way is because at this stage I could have just kept my square completed and have that as 25 minus 9, and then I could have just solved it like that. It might have been a bit easier, because that would be 16. Square rooting would have given me 4, and then adding on 1 and then dividing through would give me the 5 over 2. Oh well, you live and learn. And we move on. Oh, beautiful. Ladder question. Everyone's favourite. Certainly my favourite, actually, but maybe not everyone's. Okay. You've got this ladder, so 6A, you've got a rod here. I mean, all the information's on the diagram, really, other than that there is a mass, or the ladder has mass, so therefore we have to draw that on. I think I'm going to draw do my force diagram on this diagram here. So first off, I'm going to draw that coming down there, and that's mg. It says the end of the ladder is on a rough horizontal ground. So the ladder wants to slip down this way. So there's going to be friction here, keeping the ladder from slipping down to the left. So there's a frictional force there. There's always a normal reaction, which I'm going to call R, where the ladder hits the floor. We've also got a reactional force from this object C, so it's always going to come out perpendicular like this. I'm going to call that one N. And I think that's all the forces. We need to now take some components. So as always, I draw a perpendicular down, where this angle is the same as the slope, and this is going to be mg cos alpha. And then we've got this one coming down here, which is going to be mg sine alpha. And then I'm going to also take components of this N force at the top. Now, you'll notice that this angle's alpha. If I were to draw a line across like this, then this would make a Z to make that alpha. If I were to draw a dotted line coming up like this, then you'll notice that this angle in here will also be alpha. And that's because this angle in between them will be the complement of alpha. That will be 90 minus alpha. So therefore, the other side will be alpha. Okay, so now that we've ascertained that that angle in there is alpha, I can draw another line coming across like this, and this one will be n sine alpha because it's opposite the angle, and this will be n cos alpha. Right, I'm pretty happy with all those forces. Everything's resolved, so we should be able to, everything's like put into components, should I say. We're given that sine alpha equals 4 over 5, so they've given us another angle triangle which we can make. So I'd always recommend doing this rather than just like working out the angle itself. So it says sine, which is the opposite over the hypotenuse. That's a 3-4 triangle, so that's going to be 3. So we know that sine alpha is 4 over 5, and that means we also know that cos alpha is 3 over 5. Okay, what else do we have? Coefficient is mu, the ladder rests on the ground. So show that the magnitude of the force exerted by the ladder on the rail is at C. So I'm looking for essentially the force that I've labelled N. Okay, we take moments at A. So moments at A, it's going to cancel out lots of our forces. So we're going to go along A, we're going to go along and we're going to trundle along and we're going to hit our first force. And the perpendicular distance, the force that acts perpendicular to that distance, should I say, is mg cos alpha. So we're going to write mg cos alpha, and that's multiplied by the distance, which is half of the overall rod, so that is 3a. So that's going in that direction, and then what we're going to do after that is we're going to trundle along, and we're going to hit our next force, and we want the force going perpendicular to that distance, which is n itself. So that's equal to n multiplied by that distance, and that distance is, well, if I draw another triangle and the height of that is 4a, and I know that that is alpha, so, and I know that sine alpha is 4 over 5, then by the same logic that's going to be 5a, the hypotenuse, and that's going to be 3a for the cosine. So that distance is actually 5a going along that ladder. So I times it by 5a. So therefore we can resolve for n, and that's going to be mg cos alpha is 3 over 5 multiplied by 3a, and then just divided by that 5a. We've got a 3 and a 3 makes a 9, and a 5 divided by 5 is a 25. The a's will cancel, so we have 9 over 25 mg as required. It next says, hence or otherwise find the value of mu. Okay, the value of mu. I'm going to get rid of this working here. Just give me a bit of space. I want to keep the diagram in view. Now, what the first thing we know is that because it's in limiting equilibrium, friction is equal to mu r. So if I wanted to find mu, I would need to find the friction divided by the reactional force. Okay, so let's look first off at the horizontal forces and see what we have in total. So we've got friction acting one way. Mg is perpendicular, so that could be completely disregarded. And we've got n sine alpha working that way. So those are the only horizontal, so they must be balanced. So I know that F is equal to n sine alpha. And I know what n is, but I'm just going to keep it like that for now, just for simplicity. Okay, now let's look at the the vertical forces. again, they need to be balanced. So I've got R, I've got mg going in the opposite direction, and I've got n cos going up. So I've got R plus n cos must equal the one going down, which is mg, which means that R is equal to mg minus n cos. So now I've got an expression for f and I've got an expression for R. I can then work out my expression for mu. So I could write that mu is equal to f, which is n sine alpha, over mg minus n cos alpha. Now we know what all these things are. I've got rid of my alpha triangle, but it was that sine was 4 over 5, so cos is then 3 over 5. And we know n, because we worked it out previously, it's 9 over 25 mg. So I could write this as 9 over 25 mg multiplied by sine, which was 4 over 5, all over mg minus n, which is 9 over 25, multiplied by cos, which was 3 over 5. Sorry, 9 over 25 mg. Okay, so the mg's will cancel out of everything, and that'll leave me with just 1 there. So the calculation I need to do is is 9 over 25 multiplied by 4 over 5, 1 minus 9 over 25 multiplied by 3 over 5. 18 over 49. So mu equals 18 over 49. Oh, loved that. Absolutely loved that. 10 marks in the bag. Tell me a maths YouTuber who does ladder questions better than I do. I'll wait. Okay. Question number 5. Okay, question number 5 is a projectiles question, and the first thing I would do is I will put on my components of the initial velocity. So we've got u here, and that'll be cos 45, and then we've got this one coming upwards in the vertical, that will be u sine 45. And we are told bits of information. We know that it's travelled 100 meters. We know that it starts 25 above the ground, and that's about it really. And then it just says show that u is equal to 28. Well, let's get some equations in the horizontal and in the vertical. So we'll do a suvat in each. So the initial velocity in the horizontal was u cos 45, and we know that it could travel 100 meters, and the acceleration in the horizontal is always 0 because there are no forces acting horizontally when we do projectile modelling. And the t we don't know yet, so let's call that capital T. And we certainly don't know what the velocity is when it hits the ground. In the vertical, we know that it's gone from the top of the cliff right down to the bottom, so it's dropped down 25. The initial velocity was u sine 45. V again we won't know, and the acceleration in the vertical is minus 9.8 due to gravity. And again, t is going to be the same as it is in the horizontal, because we're analysing this particular point right here in the motion. So the ball's going to go whoop, and it's that point we're analysing, and at that point of course the time is going to be the same in the horizontal and the vertical, which allows us to solve simultaneously. Okay, so let's put together some s equals ut plus a half at squared. Okay, so for the horizontal we'll have 100 is equal to u cos 45 and we will also have it multiplied by t, and then there's no acceleration, so that's it. And for the vertical we'll have minus 25 is equal to u sine 45 t, but there is acceleration and we'll half it to get minus 4.5 multiplied by t squared. Okay, so we're going to have to find a u, so we're going to have to solve simultaneously, so we're going to have to eliminate t. So I'm going to write the x equation as t with t the subject, so 100 over u cos 45, and then I can substitute that into the y equation, which is minus 25 is equal to u sine 45 multiplied by t, which is now 100 over u cos 45, and that's going to be minus 4.9 t squared. So t squared is going to be 100 u cos 45 squared. Okay, this is not looking pretty at the moment, so we're going to have to do a bit of rearranging. The first thing I can spot is that we've got a sine over a cos here, and of course sine over a cos is tan, and tan of 45 is equal to 1. So that's going to be helpful. Essentially those two are going to cancel. And we've got u divided by u, which is also going to cancel. So we've just got 100 there. So we can minus that from this side to get minus 125. Okay, next we can divide minus 125 by minus 4.9. To get this 1250 over 49, and that's equal to 100 over u cos 45 squared. We can square root both sides, so if I take the square root of this, I get 25 root 2 over 7, 25 root 2 over 7, and that's going to equal 100 u cos 45. We could do a bit of rearranging to get that u cos 45, so multiply that to this side. The 7 could times by the 100 to get 700. And then we could divide through by the 25 root 2, like that. So we get 700 divided by 25 root 2 gives me 14 root 2. So this is very good. So that's equal to 14 root 2. And cos 45 is 1 over root 2, so dividing by 1 over root 2 is the same as timesing by root 2, so I get 14 root 2, which is 28. Bingo. Find the greatest height of the ball above the ground. Okay, well that's vertical, we're looking at height. And we're going to look at the SUVAT again in the vertical. We'll always have minus 9.8 in the vertical. We now know the initial velocity is 28 sine 45. We are looking for the maximum height, and that happens when the velocity is equal to 0. Because the ball goes up, it stops, and then it comes back down again. And we are looking for that distance, so s, so we're doing the one without a t, which is v squared is equal to u squared plus 2as. V squared is 0, u squared is 28 sine 45 squared. Well, that's not right. I'm not sure what's going on there. Hold up. 28 sine 45 is 28 times by 1 over root 2. So if I wanted to square that, then that's going to give me 28 squared over 2. So that's what I'm looking for. 28 squared divided by 2, which is 392. Don't always trust your calculator. 2 times minus 9.8 is minus 19.6 times by s, so s is therefore equal to 392 over 19.6, which is divided by 19.6, 20. Be very careful though, because is that going to be the height off the floor, or is that the height from the cliff top? And the question asks above the horizontal ground. So therefore we've got to add on the so the height is the cliff top plus the extra it's been thrown up, so 45 meters. And then we have been asked that the model is been refined, and it's going to include air resistance. So we know that the new value must be larger than 28, because for it to get the same distance to 100, but it's got a force acting against it, well then you're going to have to throw it harder. So the new value is going to be more. And then one final refinement, you could say that the object could be modelled as a ball rather than a particle. Or that the object could be spinning, and that could be modelled as well. So those are the two possible options. And that's us done. I hope you enjoyed that mechanics paper. I thought it was a good one. That ladder question, that was a beauty. And if that's not worth a subscribe, a like and a share, I don't know what is. So please do that, that'd be great. And I've got more videos on A-level coming soon, so stick around. Thank you very much.